Hello, in this video I'm going to go ahead and talk about transforming exponential functions and alternating the b value. Now our objective for the day is students will be able to determine if a base will produce, keeps jumping, if a base will produce exponential growth or decay. Please remember to go ahead and write down the objective for today. It keeps wanting to jump. Alright, so for prior knowledge, remember yesterday or today we talked about determining if the graph of a function produces a vertical stretch or a compression. So, this thing is messing up, so pardon that. Let's jump in. I want to know if g of x is an example of stretch or compression. So here I have f of x, that's my blue function, my parent function, and I have g of x, which is 3 times 2 to the x. So notice my coefficient, my a value is 3, and then it's also pulling away. It's pulling away from the x-axis. So this is an example of vertical stretch because my a value is bigger than 1. Additionally, if we just have the function itself here, I know that this is an example of vertical compression because my a value, right, is between 0 and 1. 0.5 is between 0 and 1, and however you write that is completely okay. So that is in your prior knowledge. I also want to remind you that if I have a general function here, f of x equals 2 to the x, that the 2, anything attached to the exponent, is your base value. So that's your base is always attached to the exponent, and here my y-intercept 0, 1 is found in a graph and a table. So looking at this, if the base is always attached to my exponent, b to the x, the b, and sorry, I want to activate this too, that our general exponential function is a times b to the x. What is the base value here for this function? G of x equals 3 times 0.6. Well, hopefully you noticed the base is always attached to the exponent. They're always together. So here in this situation, 0.6 would be our base. Now today we're going to talk about exponential growth, and exponential growth is when I have an exponential function and the rate of change increases over time. The rate of growth becomes faster as time passes. So notice here I'm at 0, 1, and going to this point here I rise 1 and I run 1. So that's about a slope of 1. But my next point up here, notice that I rise 2 and I run 1. So it becomes faster and faster as time goes on, and you can see that here, that I have 1, 3, 9, 27, 81. So here they're multiplying by 3 each time, and I would like that you would recognize this as a geometric sequence that we've been working with. A non-example would be this straight line. Notice this is not exponential growth because the rate of change is not increasing, it's a constant function. Please make sure you have this in your notes. The other definition we're going to talk about is exponential decay, and this is kind of the opposite of exponential growth. So exponential decay is when the rate of change decreases over time. The rate of decay becomes slower as time passes. So notice as I move here from, let's look at 1 to negative 1 to negative 0.5. Here my rate, right, is about maybe 1, say that the slope is a negative 1, whereas if I come down here and I'm looking at from 1.5 to 2, notice that that rate of change is much lower, that we only decreased not even half a value, right, on our y-axis. And we can see this here. So this is a exponential decay function, 25, 5, 1, 0.2, 0.04. Right here we're multiplying by 1/5. Our r value is 1/5. We're dividing by 5. A non-example would again be here, is if my outputs are constant. My outputs, I only have 1, 1, 1, 1. These are all exponential decay functions where we're going to be decreasing. Okay, this is a constant function. So what I would like to do first is I would like you to identify if this is exponential growth or decay, and I just want you to kind of think about this in your head before I share. But notice here I have a function that's going up. It's increasing at an exponential rate. So is this growth or decay? Well, hopefully you said I know this is an example of exponential growth because the rate of change is increasing. Here in a table form, these are our output values. So I go from 25 to 5 to 1 to 0.2, 0.4. Notice that these values are decreasing. So would this be growth or decay? Well, all of the values, my rate of change is decreasing. Right? Our values are going down. We're decaying. So this is exponential decay because the rate of change is decreasing over time. Here is this exponential growth or decay, and I can look at my outputs. All the outputs are 212. Well, this is kind of constant, right? I'm not increasing nor am I decreasing, so this is neither. I know this example of neither because the function's not increasing or decreasing. So what I'd like to do is I'd like to show you a couple of examples of exponential growth and decay on Desmos. Now, maybe at this point this is where you can pause and follow along, or you toggle between tabs. But I put the link for this map, for this graph inside your Google Classroom, so you can go ahead and look at that. And the examples I would like you to look at, here I have my parent function, f of x equals 2 to the x, and I'll set my b value to 2 so they're on top of each other. Okay, here I have my parent function, and my red function, this is my transformed function. Let me make this a little bit bigger. Okay, so I have my function, and watch what happens as I change b. So as I change b, notice that my graph becomes much steeper. So this is all exponential. This is exponential growth, right? I am increasing. So I'm still growing, still growing, still growing, still growing. So let's say f of x equals 2 to the x. This is exponential growth. So what we're going to want to do, we're going to write here exponential growth, f of x equals 2 to the x. Additionally, let's go ahead and bump it up to 3. So notice f of x equals 3 to the x. That this still, right, is exponential growth. So I have f of x, let's say g of x equals 3 to the x. Okay, so those are all exponential growth. And I'm going to punch in another one too. I'm going to say k of x equals 7 to the x. Notice that this one becomes, right, even more steeper. So this is exponential growth. Exponential growth. So I say here k of x equals 7 to the x. Now we get exponential decay. I'm going to close this out. We get exponential decay, and that looks like this, right? We're decreasing at 0.75. So 0.75 to the x power. This is decay. So I'm going to say f of x equals 0.75 to the x. And I want to also look at maybe 0.5. Notice 0.5 still, that's still decay. So g of x equals 0.5 to the x. And those are decay. All these situations kind of give me decay. Now there is a special case. I have a special case here when my b value is 1. Notice if my base value is 1, anything 1 to the power of anything, that's always going to be 1, right? Your output's going to be 1. So this is one of those constant situations. So maybe, let's say, g of x equals 1 to the x. And then some other weird stuff happens too when we put in negative numbers. So if I put in -1, so I got to name it k of x. K of x. Man, what's going on? Ah. Okay, sorry. K of x equals -1. to the power of x. So notice you don't see anything here, but if I convert this to a table, you get points. Now why does this happen? This isn't a smooth continuous line. Well, this is because, remember, anything a negative number times a negative number is a positive, times a negative is a negative, times a negative is a positive. So notice this is an alternating sequence, and we've kind of talked about those before. So this is another special case that you'll want to write over here. Say k of x equals -1 to the x power. Okay, so our objective today is to determine if what base will produce exponential growth or what base will produce exponential decay. So looking at our notes, we need to talk about the steps to determine if the function has exponential growth or if it's exponential decay. Okay, so step 1 in your notes, please fill this in. If the base is greater than 1, then this is exponential. Sorry about that. If the base is bigger than 1, then it is exponential growth. If the base is between 0 and 1, then it is exponential decay. If it's bigger than 1, growth. It grows, right? And that makes sense. 2 times 2 times 2, that's going to grow, versus if I take a half of something, I take a half of something, I take a half of something. All those values are going to slowly decay. So make sure you have these in your notes. And please go ahead and take this time, pause the video, and read to yourself these 2 steps. Okay, so for example, here I have this example, and my base value, my b value, is equal to 2. Well, if b is 2, 2 is bigger than 1, so I know this is exponential growth because the base is greater than 1, and that's what we're going to be doing here to accomplish our objective. So please write down, I think I wanted this one, please write down this one in your notes. We have f of x equals 6 to the power of x. Well, my base value here, right, b is equal to 6, and 6 is greater than 1. So therefore, I know this is exponential growth because the b value is greater than 1. Okay. And here we have this example. F of x equals 1/2 to the power of x. Well, my b value is 1/2, and 1/2 lives between 0 and it lives between 1. So this is exponential decay because 1/2 is between 0 and 1. So notice I use different formats for responding. You can do the same. And just a couple other quick examples. Here I want you to quickly identify what's the b value in your head. Okay, so is that growth or decay? Well, it's exponential growth because my base value is 7, which is bigger than 1. Here, my base value is 2/5, and that is between 0 and 1. So this is exponential decay. Alright, so that is our lesson. We have been able to determine if a base will produce exponential growth or decay. Remember that growth comes from the base value being bigger than 1, and decay comes from when our b value is between 0 and 1. Don't forget to go ahead, like my video, subscribe, and don't forget to fill out the Google form. Alright, Schwartz of the Berg, out.